Control engineering or control systems engineering is an engineering discipline that applies automatic control theory to design systems with desired behaviors in control environments. The discipline of controls overlaps and is usually taught along with electrical engineering at many institutions around the world. The practice uses sensors and detectors to measure the output performance of the process being controlled. These measurements are used to provide corrective feedback helping to achieve the desired performance. Systems designed to perform without requiring human input are called automatic control systems, such as cruise control for regulating the speed of a car. Multidisciplinary in nature, control systems engineering activities focus on implementation of control systems mainly derived by mathematical modeling of a diverse range of systems. Modern-day control engineering is a relatively new field of study that gained significant attention during the 20th century with the advancement of technology. It can be broadly defined or classified as practical application of control theory. Control engineering has an essential role in a wide range of control systems, from simple household washing machines to high-performance F-16 fighter aircraft. It seeks to understand physical systems, using mathematical modeling, in terms of inputs, outputs and various components with different behaviors. Use control systems design tools to develop controllers for those systems, and implement controllers in physical systems employing available technology. A system can be mechanical, electrical, fluid, chemical, financial or biological, and the mathematical modeling, analysis and controller design uses control theory in one or many of the time, frequency and complex domains, depending on the nature of the design problem. There are two major divisions in control theory, namely, classical and modern, which have direct implications for the control engineering applications. The scope of classical control theory is limited to single input and single output (SISO) system design, except when analyzing for disturbance rejection using a second input. The system analysis is carried out in the time domain using differential equations, in the complex domain with the Laplace transform, or in the frequency domain by transforming from the complex domain. Many systems may be assumed to have a second-order and single-variable system response in the time domain. A controller designed using classical theory often requires on-site tuning due to incorrect design approximations. Yet, due to the easier physical implementation of classical controller designs as compared to systems designed using modern control theory, these controllers are preferred in most industrial applications. The most common controllers designed using classical control theory are PID controllers. A less common implementation may include either or both a lead or lag filter. The ultimate end goal is to meet requirements typically provided in the time domain called the step response, or at times in the frequency domain called the open-loop response. The step response characteristics applied in a specification are typically percent overshoot, settling time, etc. The open-loop response characteristics applied in a specification are typically gain and phase margin and bandwidth. These characteristics may be evaluated through simulation including a dynamic model of the system under control coupled with the compensation model. In contrast, modern control theory is carried out in the state space, and can deal with multiple input and multiple output (MIMO) systems. This overcomes the limitations of classical control theory in more sophisticated design problems, such as fighter aircraft control, with the limitation that no frequency domain analysis is possible. In modern design, a system is represented to the greatest advantage as a set of decoupled first-order differential equations defined using state variables. Nonlinear, multivariable, adaptive and robust control theories come under this division. Matrix methods are significantly limited for MIMO systems where linear independence cannot be assured in the relationship between inputs and outputs. Being fairly new, modern control theory has many areas yet to be explored.
Scholars like Rudolf E. Kalman and Alexander Lyapunov are well known among the people who have shaped modern control theory. Control engineering is the engineering discipline that focuses on the modeling of a diverse range of dynamic systems, for example mechanical systems, and the design of controllers that will cause these systems to behave in the desired manner. Although such controllers need not be electrical, many are, and hence control engineering is often viewed as a subfield of electrical engineering. However, the falling price of microprocessors is making the actual implementation of a control system essentially trivial. As a result, focus is shifting back to the mechanical and process engineering discipline, as intimate knowledge of the physical system being controlled is often desired. Electrical circuits, digital signal processors and microcontrollers can all be used to implement control systems. Control engineering has a wide range of applications, from the flight and propulsion systems of commercial airliners to the cruise control present in many modern automobiles. In most of the cases, control engineers utilize feedback when designing control systems. This is often accomplished using a PID controller system. For example, in an automobile with cruise control, the vehicle's speed is continuously monitored and fed back to the system, which adjusts the motor's torque accordingly. Where there is regular feedback, control theory can be used to determine how the system responds to such feedback. In practically all such systems, stability is important, and control theory can help ensure stability is achieved. Although feedback is an important aspect of control engineering, control engineers may also work on the control of systems without feedback. This is known as open-loop control. A classic example of open-loop control is a washing machine that runs through a predetermined cycle without the use of sensors. At many universities around the world, control engineering courses are taught primarily in electrical engineering, but some courses can be instructed in mechatronics engineering, mechanical engineering, and aerospace engineering. In others, control engineering is connected to computer science, as most control techniques today are implemented through computers, often as embedded systems, as in the automotive field. The field of control within chemical engineering is often known as process control. It deals primarily with the control of variables in a chemical process in a plant. It is taught as part of the undergraduate curriculum of any chemical engineering program and employs many of the same principles in control engineering. Other engineering disciplines also overlap with control engineering, as it can be applied to any system for which a suitable model can be derived. However, specialized control engineering departments do exist. For example, the Department of Automatic Control and Systems Engineering at the University of Sheffield and the Department of Systems Engineering at the United States Naval Academy. Control engineering has diversified applications that include science, finance management, and even human behavior. Students of control engineering may start with a linear control system course dealing with the time and complex S domain, which requires a thorough background in elementary mathematics and Laplace transform, called classical control theory. In linear control, the student does frequency and time domain analysis. Digital control and non-linear control courses require Z-transformation and algebra respectively, and could be said to complete a basic control education. Originally, control engineering was all about continuous systems. Development of computer control tools posed a requirement of discrete control system engineering, because the communications between the computer-based digital controller and the physical system are governed by a computer clock. The equivalent to Laplace transform in the discrete domain is the Z-transform. Today, many of the control systems are computer-controlled, and they consist of both digital and analog components. Therefore, at the design stage, either digital components are mapped into the continuous domain and the design is carried out in the continuous domain, or analog components are mapped into discrete domain and design is carried out there. The first of these two methods is more commonly encountered in practice, because many industrial systems have many continuous systems components, including mechanical, fluid, biological and analog electrical components, with a few digital controllers. Similarly,
The design technique has progressed from paper and ruler-based manual design to computer-aided design and now to computer-automated design or CAUTOD, which has been made possible by evolutionary computation. CAUTOD can be applied not just to tuning a predefined control scheme, but also to controller structure optimization, system identification and invention of novel control systems, based purely upon a performance requirement, independent of any specific control scheme. Resilient control systems extend the traditional focus of addressing only plant disturbances to frameworks and attempt to address multiple types of unexpected disturbance. In particular, adapting and transforming behaviors of the control system in response to malicious actors, abnormal failure modes, undesirable human action, etc.